Good morning, everybody. So, I am Cédric Villani, director of the Institut Henri Poincaré, just a few meters away from here. I'm very glad and very honored to welcome you today in this beautiful, large, historical lecture hall, kindly provided by the Institut Oceanographique. And so, I'm starting recalling that last week was a quite sad week for mathematics, since two prominent mathematicians of considerable influence passed away on the same day. This was Vladimir Arnold and Paul Malliavin. Arnold was a great admirer of Poincaré, and I'm sure he would have loved this conference. Actually, last time I saw him was attending an unusual fashion show dedicated to Poincaré in presence of Bill Thurston and other distinguished mathematicians. So we will miss him dearly, as we will miss Paul Malliavin, who happened to be a personal friend of mine. Now, life of mathematicians, as life of everybody, as we know, is full of sorrow and happiness, entangled together in an inextricable way. And today we are gathered here for a very happy occasion, which is celebration of solution of the Poincaré conjecture, problem which has been with us for a century. So I'm very honored to introduce you now to President of the Clay Mathematics Institute, who has come here specially for the organization of this historical day, Jim Carlson.
Thank you. Thank you, Cédric. Thank you to the Institut Poincaré for your hospitality and your help with organizing this event. This is indeed a historic occasion. The Poincaré conjecture is something that has motivated the development of topology and perhaps I should say analysis and geometry for a century. And we are here today to celebrate the solution of that conjecture by Gregory Perelman. We're running a little bit late, so I will say just a few words. The Clay Mathematics Institute was founded in 1999 through the foresight, vision, and generosity of Landon T. Clay, who is with us here today. The Clay Institute is devoted to fostering the increase in mathematical knowledge and its dissemination. So without further ado, I would like to introduce Andrew Wiles, well known for his solution of another French problem, Fermat's last problem. Andrew will introduce Professor Attia. Andrew?
My pleasure to welcome you all here, especially the Clay family, on this great occasion. And it's my pleasure now to introduce our first speaker, Sir Michael Attia. Sir Michael has been President of the Royal Society, Master of Trinity College, founder of great schools of geometry and topology in both Oxford and Cambridge. And that's not to begin to speak about his illustrious mathematical career, which includes, of course, the index theorem, of which he was co-author and named after him. He is currently honorary professor at Edinburgh University, and he will speak on geometry in 2, 3, and 4 dimensions.
Thank you, Andrew. This is a very special occasion. In the days of Shakespeare, before the play started, there was something called the prologue. Somebody went on the stage to warm up the audience, get them ready, fit in the right mood, and then the play would follow. I am the Shakespearean prologue. My title, as you see here, is Geometry 2, 3, and 4 dimensions. And I think when you're giving a general talk to a large audience, it's important that at least the title should be understandable. And I hope you understand most of the words in that title. Now, this is advanced technology. I may press the wrong button. There we are. So this is the Clay Institute Millennium Prize that we're celebrating. And the two figures you see here are, of course, the two main actors. Henri Poincaré, the great French mathematician, who died just under a century ago, and who made the conjecture, which we are celebrating the solution of today, and Grigory Perelman, the young Russian mathematician who has solved it. As you'll see from the dates given, Perelman wasn't even born more than 50 years after Poincaré died. So mathematics has a long gestation period. Problems last a long time, they take a long time to solution. You mustn't be in a hurry. These days, people tend to be in a hurry. So, I want to talk about this conjecture now. This is a summary of what I want to say. I've been given a very short timetable, so it'll be a quick summary. First of all, I want to say something about the historical context. Now, I think history is always very important in everything. As individuals, our personality resides entirely in our memory. If somebody loses their memory, they lose their personality. The same is true of civilization. Without our knowledge of our past, we really are nothing at the present. And that applies in particular to mathematics. So you must always understand the historical background of any part of mathematics, any problem, where it's come from, how it progresses, and where it might lead to in the future. So history is crucially important, and I want to spend some time in very general terms about the historical context of the Poincaré conjecture. Secondly, mathematics is not unconnected with the real world, I'm glad to say. And in particular, it has a very strong, intimate and long relationship with physics, which is very pertinent in the context of geometry and of the analysis that often goes with it. And that certainly is true of the Poincaré conjecture. And then, just as the past is important, so the future is important, although the future is a little harder to predict. And so I want to say a little bit about where we go from the Poincaré conjecture, or point toward directions where the future may lead. And, of course, the other speakers in this two-day conference will deal with more detail with all these aspects. Mine, as I said, just the warm-up act. So, geometry, history of geometry, starting with the ancient Greeks, was mainly originally about straight lines and planes and flat surfaces. But by the time of the 19th century, end of the 18th century, people were studying curved surfaces, surfaces which were curved, like the curved surface of a sphere, but curved not necessarily in a uniform way with bumps. And the history of geometry since then has, to a great extent, been the study of the notion of curvature. What is curvature? How do you define it precisely? What does it mean? And how does it change as you increase the number of dimensions you have? In dimension 1, along a straight line or on the edge of a circle, there is no real geometry. All you can do is to measure how far along the path you are. Geometry starts in dimension 2. And it was Gauss, in the 19th century, who defined what we now call Gaussian curvature, or the scalar curvature of any surface. It's a number which varies from point to point, measuring a certain notion of curvature. For example, a sphere has constant curvature always equal to some number defined by the radius. And this is a notion of curvature which is called intrinsic curvature, to distinguish it from extrinsic curvature. For example, although the sphere, you know, is curved, and curved intrinsically because you can't draw a precise map of the atlas of the world on a piece of paper without distortion, if you have something on a scroll, like these Chinese scrolls you unroll, or a piece of Christmas wrapping paper you buy, you unroll that, there's no distortion. A cylinder looks curved, but it's actually flat from the point of view of Gaussian curvature. It's curved in one direction, but not in the other, and it's important that both change. So the 19th century was, which started off with Gauss and went on, was the development of the notion of curvature in 2 dimensions by one function called the scalar curvature. In the 20th century, we moved on from 2 dimensions to 3 dimensions. This is a very abbreviated, shortened, history does not actually follow centuries exactly. So give or take 20, 30 years. Allow me a little latitude. The 20th century, you can say, well, the 19th century finished with a very, very deep theory of 2-dimensional surfaces in all aspects, geometrical, analytical, complex, real. The 20th century, you might say, was devoted to the ideas of 3-dimensional geometry, and this is the culmination of it today, a little bit after the end of the 20th century. And then in 3 dimensions, the curvature is more complicated than 2 dimensions. It's determined not by a single number r, but by a number r that depends on 2 directions, I and j, called the Ricci curvature. And when you go to 4 dimensions, and 4 dimensions is very, very important, even if you don't believe in it, there are a lot of ways in which 4 dimensions affects our world, especially if you include time. The that is now, in some sense, the center of attraction for mathematicians in the 21st century, and it may be not until the end of the 21st century that is better understood. And here, the curvature first introduced by Riemann depends on 4 indices or 4 directions. So this is, and it's after that situation has changed. It doesn't get more complicated in 5 and more dimensions. It becomes simpler. These are the dimensions of interest. Now, 2 dimensions. Let me go back to the history of 2-dimensional surfaces. The great names. Now, I like to talk about names and show pictures of people to emphasize that mathematics is created by individual people, and people with real names, real faces, and real personalities. So this talk is essentially showing slides of famous people, and that's actually also easy to understand. Now, on the left, we have the great Gauss, who lived a long time, as you see, did many things in mathematics, but in particular laid the foundations for modern differential geometry. Then we have the very young, sadly tragic early death of Niels Henrik Abel, the Norwegian mathematician, who just studied algebraic equations, showed for the first time that equations of degree 5 and more cannot be solved in terms of radical square roots and so on. And he was brought into the theory of geometry, the complex variables that arise in polynomial equations. And then the last name in this figure is great Bernhard Riemann, who did many, many things in life, whose collected works occupy 1 slim volume, but each chapter in that covers whole regions of mathematics. And he brought the modern notion of topology into the game to add to the differential geometry and the algebraic geometry of Gauss and Abel. These are, with regard to the 3 great figures in the history of geometry in the 19th century. If you look at the dates, you'll see that Gauss lived more than Abel and Riemann put together. But age does not alone define fame. Now, Riemann surfaces, our 2-dimensional study, is a very simple story. The surfaces are all characterized topologically by one number called the genus. When the genus is 0, the surface is the surface of the sphere. When it's 1, it's the surface of a torus, a ring. And when it's greater than or equal to 2, that's everything else. And these surfaces, you can have on them metrics describing geometry, and they are characterized by being 0 curvature in the case of the torus. The torus is flat, in a sense, like a cylinder. And the sphere, which has positive curvature, which curves one way, and the surfaces of negative genus, which curve the other way, where the Gauss curvature takes values either 0, plus, or minus. And there, in green, is a typical picture of a surface of genus 3. The genus is the number of holes, and everybody can see there are 3 holes there. The sphere has no hole, it has inside. The torus is a sphere with a hole bored through it. So that is, in summary, the topology of Riemann surfaces, and from the topology, on the topology, you build a very elaborate superstructure involving complex numbers, polynomial equations, all sorts of other things. This is the start, in one sense the end, in the other sense the start of the theory of surfaces. That was fully understood by the end of the 19th century. Now, in 3 dimensions, you have a new world. First of all, an important fact to remember is that 3 is an odd number. 2 is an even number, 3 is an odd number, 4 is an even number, and the theory in geometry in even odd dimensions is very different. One of the reasons it's different is that geometers also like to use, besides real numbers, complex numbers, like square root of minus 1. And when you have complex numbers, the dimensions always double. So complex dimension, real dimension 2 is related to the theory of complex variables, one complex variable, ordinary polynomial equations in one unknown. Theory of polynomial equations in 2 unknowns leads you to 4 dimensions. 3 dimensions doesn't have any direct relationship with complex numbers and is therefore fundamentally different. But one should say that when you look at consecutive dimensions, they are tied together. If you have a surface, it may have a boundary, which is 1-dimensional. If you have something 3-dimensional, it will have a boundary which is 2-dimensional. If you have something 4-dimensional, it will have a boundary which is 3-dimensional. So successive dimensions are related by the notions of being boundary. So the geometry does go together, but there are basic differences. Now, in Dimension 2, the fundamental notion of the genus, which consisted in counting the number of holes. When you go to more dimensions, there's a fully developed, well-known mathematical theory which counts holes in a similar way, except you can have holes of different dimensions, and that goes under the name of homology. And Poincaré was one of those who founded that theory. But Poincaré also discovered something else, that wasn't, when you go from dimension 2 to 3, there was something appeared which did not happen in dimension 2. That was the notion of what called the fundamental group. It consists of what you taking closed paths in the space, deforming them around, regarding those as the same, and when you go around one path and follow by another path, you get a composition law which makes what mathematicians call a group, and you got a fundamental group, and the group you get can in general be not a commutative group, and it was his failure, first of all, to realize this that led him to make a incorrectly think he'd solved the Poincaré conjecture before he had. And the example that he realized that he got something that looked like a sphere from the point of view of homology, but was not, can be built out of the beautiful, regular Platonic solid, the icosahedron. Interestingly enough, the symmetries of the icosahedron, which are non-commutative group, order 60, that also is the same non-commutative group that occurs in the proof that the quintic equation is insoluble and when it goes back to Abel. So there's a very direct link between the insolubility of quintics and the fake sphere of Poincaré in dimension 3, and similar reappearances of the icosahedron in dimension 4. So these beautiful gems of antiquity, like the icosahedron, persist throughout the history of mathematics. Well, you'll hear more about that later, but the point is that the fundamental group is something which is new in dimension 3, didn't really exist in dimension 2 except in a trivial way, and is the heart of three-dimensional geometry. Now, the Poincaré conjecture, which he made properly after he realized his first mistake, said that if you have a three-dimensional manifold which has no group, trivial group, and then it's called simply connected, every path can be shrunk to a point, then that manifold has to be a sphere. He thought it was inevitable, but he couldn't prove it, of course, and it has taken 100 years to prove. So that was the Poincaré conjecture in a nutshell, how it fitted into the history. And while people were working on that, many things happened. People didn't give up. They tried other things. They tried to generalize what would happen, what was the analog of the higher genus surfaces. And Bill Thurston, who is here, will talk later on, he put forward this very ambitious program about how every three-dimensional manifold could be built up out of manifolds of different types. And just like in two dimensions there are three types, curvature 0, positive, negative. In 3 dimensions, there are, I think, 8 types, determined by the kind of fundamental group they have, more than just by number. You start off with a sphere, which is the case of positive curvature. The other extreme, you end up with what's called hyperbolic manifolds, totally negative curvature. And in between, there are various mixed types. And he put forward a big program to what geometry should look like. And did a lot of work showing that actually was highly plausible. Well, Perelman's proof for the Poincaré conjecture is by such fundamental methods that it has extended to enable the full Thurston program to be achieved. So this is the end of an era. A lot of work has gone on, culminating in this great theorem, which not only proved the conjecture of Poincaré, but proved the much larger panorama view that Thurston had outlined. So that certainly deserves not only a prize, but a conference to celebrate the prize. Now, I said I would talk about the past, but I also have to say something about other things, the relation with physics, and the future. So let me just go a moment to talk about complex algebraic geometry. I told you that complex equations, polynomial equations in one variable, led to the work of Abel, Riemann, two-dimensional surfaces, Riemann surfaces. But people also studied what happens when you have more than 2 variables. Then you get algebraic varieties of dimensions more than 1 complex variable, maybe in general n, and then 2n dimensions real. So you miss out 3. So this is going off in a different direction. It's taking the theory of Abel and Riemann and pushing it forward in the direction of even-dimensional theories related to algebra. Now, the great names in this subject I've listed here are, first of all, Solomon Lefschetz, very powerful figure in the world of mathematics in his time, who laid the foundation of a lot of topology after Poincaré, and also of applications to algebraic geometry, and he was a major figure in that period. After that, there was William Hodge, my own supervisor. By the way, my memory doesn't go far enough back. I didn't actually know Poincaré. I'm old, but not quite as old as that. But I did know Hodge, I did know Lefschetz. Hodge, his contribution was to bring analysis, very similar to the analysis that Riemann had used, to bear on complex algebraic geometry in general, and to refine the work of Lefschetz, and laid the foundations of what is called Hodge's theory, which had been fundamental for geometry and physics of the 20th and 21st centuries. That was very major progress in algebraic geometry. And then in the second part of the 20th century, in the post-war period, the main development was what is called sheaf cohomology, which was a kind of marriage between topology and analysis. You took the techniques of analysis by studying things locally, you piece them together in the large by methods of topology and homology, and you got this very flexible, powerful tool called sheaf cohomology, much of which was developed here in Paris. And two of the key figures are there. Some of you may not recognize the young man on the right, Jean-Pierre Serre. I knew him when he was quite young, but not quite as young as that. I think there he is still a graduate student of Henri Cartan, whom I also knew, who died not long ago at the age of 104. But I didn't know Cartan quite as young. But Serre, I didn't know. I think there he is probably about 20 or 21, something like that. Anyway, not many people remember him like that. But he's one of the modern generation. As you see, he doesn't wear a tie. He only put on ties for very important occasions. Perhaps today he would have had a tie. Now, that was telling you about what's happened in complex algebraic geometry in higher dimensions, and there's a full story there which I can't go into. But if we focus on the real dimension 4, that occurs on the one hand as complex dimension, two complex variables, part of the theory of Hodge and sheaf cohomology and all that, but also it takes into account four-dimensional manifolds which do not arise from algebraic equations. In dimension 2, every Riemann surface arises from an algebraic curve. In dimension 4, it is not true. Trivially, it's not true. Even the four-dimensional sphere does not come from algebraic equations. Nevertheless, algebraic geometry plays an important part in real four-dimensional geometry. But there are new features. And this is, of course, the era not of my teachers, but of my students, or generalized students. And two of the key names here, who I've showed you pictures of, well, one of them lives in California, and you can guess who he is from the background, from the shirt, the tea mug, the agapanthus, and the blue skies. That's Michael Friedman, who proved the topological theory, which implied in particular the Poincaré conjecture in dimension 4 in topology. But almost simultaneously, Simon Donaldson, who was my student, one of the speakers here today, showed that when you worry not about continuity, but about differentiability, having things smooth, whereas in dimension 2 and 3 that's the same, in dimension 4 is different, and totally different phenomena appear in dimension 4. For example, the Poincaré conjecture for a smooth four-dimensional sphere is not, I believe, yet solved. Another prize for the Clay Institute, no doubt. And there are totally new phenomena. Now, the one I'd like to single out, which follows from the work of Donaldson and Friedman, is that if you look at algebraic surfaces, two complex variables, or four real variables, in the case of dimension 2, Riemann surfaces, you can remember the picture, are made up of things with holes. And you can think of something with two holes as being got by taking two things with one hole, two tori, and putting a little bridge between them and gluing them together. And you can do that with any number of holes. Every Riemann surface can be built up by adding a suitable number of copies of the basic one with one hole, the torus. That's not true in dimension 4. And Donaldson showed beautiful examples, algebraic surfaces which you cannot decompose by smooth methods, although you can decompose them brutally by topological methods. And this is totally unlike what happens in 2 dimensions, and there's a very deep theory here. We're still at the early stages. I talked to Simon just before. I was reassured that when he talks later today, he won't be telling me that this has all been solved. There are still things to be done for the young mathematicians, and I suppose there are some young mathematicians here in the audience somewhere in the back row. We'll keep you busy for the next 90 years. So that's the relation with real geometry. Now, connected with physics. Again, this is a big subject, but we're in a room which I suppose has something to do with physics, the sea and ships and so on. And in physics, there has been a spectacular development over the last 30 to 40 years, which I've lived through as more or less as a sort of spectator from the sidelines. And the key participants in that, well, the key participant is certainly Edward Witten, whose picture is up there, who is the leading theoretical physicist of our time in the views of many people, but he's also a mathematician with enormous talents. And he has done more than anybody else to bridge the gap between physics and mathematics. And he showed in particular that the work of Simon Donaldson, which had its origins in taking ideas, equations from physics and using them geometrically, Witten was able to show very beautifully how, in detail, the Donaldson theory could be seen or interpreted in terms of physics. It was a magnificent bridge between one and the other. He also was able to do something similar in the case of 3 dimensions. I haven't had time to mention it, but I will say something about it now, that in 3 dimensions, one aspect of 3 dimensions that is unique to 3 dimensions is that you can tie knots in 3 dimensions. If you have a closed piece of string, if you put it on a plane and you don't allow it to cross itself, then all you get is the circle. But in 3 dimensions, as you know from your shoelaces, they can get entangled, and the theory of knots is a very old part of topology. In a way, it's the most easiest part of topology to explain. When you have a knot which is tied up in a tangle, what's important is not the length of the string or the thickness of the string or the material of the string, it's simply whether it's knotted and how it's knotted, or whether one knot is equivalent to another knot or not. Sorry, that's a difficult thing to say. But the theory of knots has been with us for a long time, and a lot of progress has been made. One of the spectacular progresses was due to Vaughan Jones, whose picture is down there, New Zealand mathematician, who produced a lot of beautiful invariants, as we call them, of knots, numbers that distinguish different knots. And Witten was also able to show that this Jones theory could be interpreted in relation to quantum physics. So both the work of Vaughan Jones and the work of Simon Donaldson are linked to physics, and that is just the tip of the iceberg. There's a vast amount more behind those 2 examples. So connected with physics are extremely strong, have been for some 30 years, are still strong, and hold up promise for the future, both for physics and for geometry. Future problems. Well, what are the future? In dimension 3, well, one obvious problem is how do you relate these Jones quantum invariants, so we call them now, things that you can associate. By the way, not only are they defined for knots, but as Witten was able to show, they're defined not only in 3 space, in any 3-dimensional manifold. So they apply to the work of Thurston and Perelman. So we have 2 different theories in 3 dimensions. There's the geometrical theory of Perelman and Thurston, which describes how you build surfaces, what kind of curvature they have in terms of fundamental building blocks. And there's the theory of Jones coming from physics and quantum theory, which produces a lot of numbers which distinguish between how these numbers relate to the Thurston-Perelman structure is still very mysterious. There are clues, and I think there will be some talks later today which will tell us how far it's got. I regard this as one of the outstanding problems, because you have a theory with only one magnificent theorem is great, but you have 2 theorems, and it's not related, that's not so great. You have to build a bridge. So in dimension 3, there is a clear outstanding program there. In dimension 4, the program is even vaster because we know much less. The real question in dimension 4 is what replaces the Perelman-Thurston program from dimension 3 to 4. Understand the structure of 4-dimensional manifolds and its relationship to physics, because there is a relationship to physics. Now, in 4 dimensions, you can, of course, have a fundamental group, but the fundamental group in 4 dimensions does not seem to be the heart of the problem. The problem arises even if there is no fundamental group. If you have a simply connected 4-dimensional manifold, the important thing is that in dimension 4, the middle dimension of 4 is 2. In 3, there is no middle dimension, so if the fundamental group is trivial, there's nothing left. In 4 dimensions, what's left is the 2-dimensional homology, 2-dimensional cycles. These are like the 1 cycles in 2 dimensions, the things that go around the holes. And the structure of 4-dimensional manifolds, it seems to be deeply related to the two dimensions in the middle that we have, a new phenomenon and relation to physics. But fully understanding this will take a long time. Simon's guess is as good as mine. I think, it may take 50 years, it may take 100 years. And if you remember the Riemann curvature, the tensor I mentioned at the beginning, there is a scalar curvature in dimension 1, which is one number. In dimension 2, there is one scalar curvature. In dimension 3, there's a Ricci tensor, which has 2 indices. In dimension 4, there's the Riemann curvature tensor, which has 4 indices. In dimensions 5 and above, it still stays 4, doesn't change. And 3 and 4 are somehow the heart of the notion of curvature, which goes back all the way to Riemann. And what it'll lead to, we don't know. Now, let me end up with some more remarks about physics and some speculation. Now, I'll remind you that Einstein's great theory of gravity brought in time as well as space. And he combined space and time together. Well, it was first done by Minkowski in what's called four-dimensional space-time. But Minkowski thought of them as flat space, flat time. Einstein allowed the spaces to be curved. And using the general theory of Riemannian geometry coming from Riemann, he was able to write down equations for general relativity, for gravity, in a very beautiful, simple form, which depend basically, the Ricci tensor is 0. So there is a beautiful geometrical theory of gravity, which was developed by Einstein way back in 1915. Is that somebody's? It's all right, nothing to do with me. Okay, good. Now, a little bit further back than Einstein, there is the theory of electromagnetism developed by James Clerk Maxwell, the greatest physicist of the 19th century. And for him, he had the fundamental equations, and it was after Einstein brought in his theory of gravity, there was a natural question, which many people, including Einstein, thought about, how to combine gravity with electromagnetism, the two fundamental forces of the universe. And it was a beautiful idea, first put forward by the great German mathematician Hermann Weyl, and subsequently developed by other people like Kaluza and Klein, which says that you can add another dimension to space-time, a fifth dimension, a small circle, so to speak. And in these 5 dimensions, the geometry of 5 dimensions would include both four-dimensional gravity of Einstein plus electromagnetism, which came from the way the circle varied in space. And so you combine the two equations into one 5-dimensional picture. Beautiful unification of the geometries which were known at the time. Now, of course, combining electromagnetism and gravitation combines two of the fundamental forces of nature, but leaves aside the whole nature of the structure of matter, which is concerned with very small particles and very powerful forces at short range. And physicists have been struggling how to understand the nature of matter for the last century and how to combine it with Einstein's theory of gravity. This is currently the big program. And the speculation I offer here, as you get older in life, easy to offer speculation, you won't be around for the consequences. Somebody may solve the problem, somebody may show it's trivial, it may last 100 years. So my speculation goes like this. If you have space, which means good old-fashioned 3-dimensional space, and you add one circle, you get 4 dimensions. 4 dimensions where you can do ordinary Riemannian geometry, where you can apply Donaldson theory, 4 dimensions, and you may get models which might be useful models of matter. And if you look at the 4-dimensional geometry, it's such a rich theory, there's a lot of material there which might have physical interpretation. For example, one of the important things in physics is there is something called electric charge. And if you have a 4-dimensional manifold that represents some bit of matter, it has a number, what is called the signature, which comes from looking at the 2-dimensional cycles inside it and seeing how many intersect in positive numbers and negative numbers, elementary algebra, a number that doesn't have a counterpart in dimension 2 and plays a very important role in dimension 4, and that is a number you can associate to a 4-dimensional manifold, so why not interpret it perhaps as something like electric charge. But there are other numbers you can associate, and for a manifold you can look at all the middle homology. What is the size of the middle homology? How many 2 cycles there are? This is the analog of genus, or twice the genus. And so in fact, this you might want to interpret it not only in terms of electric charge, which for matter is described by the number of protons. Matter consists of protons and neutrons. nuclei, consist of protons and neutrons, and the protons are charged and the neutrons are not. So the number of protons give you the electric charge, and the number of neutrons doesn't change the charge, but it changes the mass. So you have two numbers in physics and two numbers in geometry, and my speculation is perhaps they're related. Well, that takes another century to prove, perhaps only 2 days to disprove. End of talk. Thank you.